Let me just recall back the statement of a theorem that you have done in third semester. We just need to apply this theorem in proving the next theorem. So now the theorem states like this: a non-empty subset H of a group G is a subgroup of G if and if for every A and B belong to H, it implies that AB inverse should belong to H. So in order to show that H is a subgroup of G, you just need to check by taking arbitrary elements A and B in H and show that if AB inverse still belongs to H, then we can conclude that H is a subgroup. So I'll use this theorem in proving this theorem on normal subgroups. And then let me just recall again the definition of normal subgroup. A subgroup H under the binary operation dot of a group G under the same binary operation dot is a normal subgroup of G if and only for every X in G and H in H, X inverse should belongs to H. See, this X must be an element of G, H must be an element of H. However, if this product X inverse belongs to H, then we can conclude that H is a normal subgroup of G. So now let me define the definition of product of two subgroups of a group. Let H and K be any two subgroups of G. Then the product of HK is defined as HK is equal to set of small h into K such that H belong to H, K belong to H. So the expression of the element of HK will be the form small h into small k, where H is the first element belongs to H and the second element belongs to K. Now, let us come to this theorem now. If N and H are both normal subgroups of G, then in that case the product also NH will be a normal subgroups of G. So if N and H are normal subgroups of G, then NH is a subgroup of G. So how to prove this one? So take N and H to be normal subgroups of G. So first thing what we need to do is we have to show that NH is a subgroup. And then secondly, we need to show that NH is normal in G. So to show that NH is a subgroup of G, what we need to do now is we'll apply this statement of this theorem. So now what is NH? NH contain these elements small n into H such that N belong to N, H belongs to H. Now here you take, for the first part, let N1 H1, N2 H2 belongs to NH. N1 H1 is an element of NH, N2 H2 belongs to NH. Now if you can consider this one as an element A and this as an element B. Now to prove that NH is a subgroup of G, I need to show that AB inverse should belongs to NH. That is N1 H1 into N2 H2, the whole inverse must belongs to NH by using this or applying this theorem. So let us now find out now what is N1 H1 into N2 H2, the whole inverse. If I can show that this element still belongs to NH, then I can conclude that this is a subgroup of G. So this is equal to N1 H1. Now N2 H2, the whole inverse is same as H2 inverse into N2 inverse. In a group we have this one AB, the whole inverse is equal to B inverse A inverse. So by applying this property, this is inverse. What we need to do now is I can introduce this element N1 H1. Now let me introduce N2 here. Here it should be N1. Then introduce N2 inverse N2 inverse N2 in between H1. Then H2 inverse N2 inverse. Just introduce this element N2 inverse N2 because N2 inverse N2 gives you E. So this is equal to N1. Now combine this one N2 inverse together. Then N2 H1 H2 inverse N2 inverse. This is N1 N2 inverse. Now this will be N2. Then take this element H1 H2 inverse as a single element, H1 H2 inverse N2 inverse. So now here this N1 N2 is an element. Here you have to note down N1 belongs to N, N2 also belongs to N. Similarly, H1, H2 are elements of H. So N1 belongs to N, N2 belongs to N, and N is a subgroup of G. So N1, N2 inverse will belongs to N. So this element belongs to N. Now what about this one? N2 is an element of N. N2 inverse also will be an element of N. Now H1, H2 inverse. H1, H2 inverse is an element of H only. This element here inside the round bracket belongs to H. Now this is of the form X, H, X inverse. See, this one is of the form X, H, X inverse, where X is N2 and X inverse is N2 inverse, and H here it is H1, H2 inverse. And since by the given definition H is a normal subgroup of G, so X, H, X inverse must belongs to H. So it means that N2 into H1, H2 inverse, N2 inverse, this whole thing will belongs to H. Now you can see that the first element, this belongs to N, and the element inside the square bracket belongs to H. So which means that this N1, H1 into N2, H2, the whole inverse belongs to NH. So which means that NH is a subgroup of G. Now next I need to show that second part is I need to show that NH is normal in G. So for this one I need to apply this definition. Take X in G and H belongs to H, but here what is H? H is the NH. So let NH belongs to NH and X belongs to G. What I need to show is that X into NH into X inverse, this belongs to NH. If I can prove this thing, then I can conclude that NH is normal in G. So now here X into NH into X inverse, this can be written as, what we need to do now, you introduce X inverse, X in between N and H. So you can write here X, then N, then in between N and H you introduce this one, X inverse X, then H, X inverse. Why? Because X inverse X gives you E, and NE into H will be same as NH, where E represents the identity element. So now here we can express this element as this one, and this is equal to X. Now take this one N here, then X inverse, combine them together, the first three elements combined together, and the last three together, XH, X inverse. Now this belongs to N. Why it belongs to N? Because N is a normal subgroup of G. This is given as this element here, N belongs to N, H belongs to H. So as N is a normal subgroup of G, so for every X in G, X and X inverse should belong to N. Similarly, H is a normal subgroup of G, so X in G and H in H, X inverse also will belongs to H. So this belongs to H. So finally it implies that X into NH, X inverse belongs to NH. So this gives you, this conclude that NH is normal in G. So on combining 1 and 2, this one, on combining 1 and 2, the first one is that NH is a subgroup, and the second part is NH is normal in G. We can conclude that NH is a normal subgroup of G. I hope it is clear now with this explanation.